Hello, everyone. Let's start. Well, as you know, this is applied real analysis, and our class is mostly about partial differential equations, boundary value problems, and partial differential equations. So there's not much to say. I think I've written almost everything I wanted to say in the syllabus. We would have a midterm and a final, and we would have weekly homework that you would upload to Gradescope. The Gradescope of the course is not ready yet. I would add you, I guess tomorrow, I would add you to the Gradescope of the course. I would encourage you to turn on your camera and interrupt me and speak and talk about whatever you think about. I do not want to just talk, and I want you also to participate. That would be great if we can do that. So I think the style of the course would be like this. I'm going to write down a differential equation, and I would give you some time just to think about it for a few minutes. And if you find the solution to the equation, you would share it with others and we would discuss it. And if not, I would write down the equation. So I think we would follow the course mostly through examples. Okay. That's mostly it. The reference for the book, well, there is a book. I think you can, well, I shouldn't say that, I guess, but well, there is a book which you can find it in the syllabus. It's not required, it's encouraged. You can get that. That's recommended, actually. You can get that book. You can read that. I'm sure we cannot completely go over a textbook. That takes a long time. So I'm going to write down lecture notes for every meeting, and I would upload them to our course page. So you can either follow the lecture notes, or if you want to solve more problems and more questions, become deeper in the course, you can look at the reference of the course. Probably I would introduce some other lecture notes and places to look for examples too. I guess you can find all these in the syllabus. Okay, let's start. Is there any question?
Will the lecture notes be uploaded before class or after class?
No, after class, because I want to see what exactly. So I do have the lecture notes, but I would probably slightly change them after each class, because I would see how much I can cover in the class, and if there is any question raised during the class, I try to kind of answer that in the lecture notes. So it would be after the class. Okay. Okay, let's start. So, okay, let's see if everything works well. Yeah, great. So we are going to, we will mostly, well, I guess if we want to follow the lecture notes I have, we are going to have 4 chapters. There would be chapter 0, chapter 1, chapter 2, and chapter 3. Chapter 0 would be ordinary differential equations. And chapter 1 to 3, they are going to be about partial differential equations. So the reason we start with ordinary differential equations is that one of the main techniques to solve partial differential equations, which are more advanced and more complicated for us, is to kind of break them and transform them into several ordinary differential equations. So ordinary differential equations, it means it's a differential equation. It has one variable. It's the derivatives are with respect to one variable. Partial differential equations means we would have derivatives with respect to several variables, as you would see. So chapter 1, 2, 3 would be there are going to be about 3 important different differential equations, which we are going to see. So let's start with ordinary differential equations. So let's start with an example. Suppose we are looking for a function y of x. So here y of x is a function of x. We are looking for y of x such that if we take derivative of y with respect to x, that's the notation we would use. That's the derivative of y with respect to x. It would be lambda times y, where lambda is just a real number. Okay, so probably you might have seen this example before. If you haven't, that's okay. We would go over that. So this is an example of a differential equation. We are looking for a function y, a function of x, such that it satisfies this equation, right? Y can be anything. It can be a polynomial with respect to x. It can be sine, cosine, log, exponential function, or anything. So, well, let's see how we are looking for, mostly we are looking for systematic ways to solve differential equations, right? Methods which we can use in different places. Well, before solving this equation has one obvious solution. This equation has one obvious solution. Okay, can anyone guess what is this obvious solution? There is a trivial solution to this equation. Well, that's not the trivial one. That is certainly correct. Yeah, that is a correct solution. But yeah, 0 is the trivial solution. If we let y of x equal 0, we get one solution for this equation. How is that? Well, look at the left-hand side. The left-hand side, we have derivative of y with respect to x, which would be derivative of 0 with respect to x. Well, obviously, derivative of 0 is 0. What is the right-hand side? The right-hand side is lambda times y, and if y is 0, well, the result of that multiplication would be 0. And therefore, as you can see, the left-hand side is equal to right-hand side. That means y of x equal to 0 is one solution to this equation. Well, we have another suggestion in the comments. That's also correct. So one person has suggested this function. Y of x equals to e to the lambda x. Let's see if this is, we are just trying, right? Let's just assume someone has guessed that this is the solution. Let's see if it is really a solution or not. So we should first look at the left-hand side and right-hand side. Let's look at the left-hand side. What is the left-hand side? We should take derivative of e to the lambda x with respect to x. So what is the result of this derivative? Well, you might know that derivative of e to the x is e to the x. But derivative of e to the, say, 2x is actually 2e to the x. And more generally, derivative of e to the lambda x for any real lambda is equal to lambda e to the lambda x. Okay, now having that in mind, let's go back to our equation. Here, derivative of e to the lambda x with respect to x is lambda e to the lambda x. What about the right-hand side? The right-hand side is lambda times y, but here we say y is e to the lambda x. And as you can see, again, right-hand side is equal to the left-hand side. So here we do have another solution to this equation. But how can we be sure that there is no other solution? Or what if we cannot guess this answer? What is the way to find the solution? Okay. So here we have dy over dx equals to lambda y. Here, what we are going to do is kind of an algebraic manipulation. This might not make much sense because you see, dy over dx is not really a fraction. It means derivative of y with respect to x. So the fact is that this is not really a fraction. But this just means derivative of y with respect to x. But for a moment, let's forget about that, okay? Let's suppose it is a fraction, and suppose we can multiply both sides of the equation by dx. If I do that, I would get dy is equal to lambda y dx, right? Now let's divide both sides by y. If I do that, I would get dy over y is equal to lambda dx. So what we did here is separating the x variables and the y variables, right? I moved all terms which they have y variables, including dy, to the left side of the equation, and everything which has x in it to the right side of the equation, right? We are separating the variables. Now, the third step would be taking integral of both sides. So if I take integral of both sides of this equation, that's what I'm going to get. Okay. Let's compute each integral. What is integral of dy over y? Does anyone know the answer? That is almost correct. Someone has said, I can see in the comments, Brandon said ln of y. That is almost correct, right?
Absolute values.
That is correct, yes. This would be ln of absolute value of y, and as Diana has said, we would have plus a constant c, right? Whenever we take integral, we would have this constant. But yeah, that is correct. What is derivative of lambda dx? Well, lambda is a constant number. I can bring it out of integral. It's just integral of dx. What is integral of dx? It's just integral of 1. But this is integral with respect to x. What is integral of 1 with respect to x? Yes, that is correct. So the integral would be just x. Again, here we would have another constant. I use c prime here. So this equality tells us that ln of the absolute value of y is equal to lambda x plus a constant. I still show it with c. It's actually c minus c prime. If we look at the notations we have before, but doesn't matter, it's another constant. So I use capital C to show that. So here we have ln of absolute value of y, but what we are looking for is y itself. So how can I get to y itself? So what I know is that ln of absolute value of y is equal to lambda x plus c. If I want to find y, I should get rid of ln. And the way to do that is to use the inverse of ln, and that's the exponential, right? So we should take exponent of the both sides of the equation. So if they are equal, e to ln of absolute value of y is also equal to e to the power lambda x plus c, right? Now, what is the left-hand side? What is e to the ln of absolute value of y? Well, the exponential map and the ln are kind of the inverse to each other. They are the inverse to each other. So the result would be just the absolute value of y. They cancel each other, okay? But that's the left-hand side. What is the right-hand side? E to the lambda x plus c. Well, we know that, we know this power rule about the exponential. It's equal to e to the c times e to the lambda x. Note that e to the c is still, it's just another constant, right? So I would show that with just d times e to the lambda x. Now, having these two things, that means absolute value of y is equal to a constant d times e to the lambda x. Therefore, y is equal to plus minus d e to the lambda x, right? If I drop the absolute value, I would get plus or minus. But it still doesn't matter because plus or minus is another constant, right? Let's just show that constant with e. So we have our solution. Therefore, that is the solution to the equation. Y is equal to a constant times e to the lambda x. That is the solution to the equation, okay? So we kind of showed that this is the solution to the equation, and these are all the solutions for different constants e. If e is equal to 0, we would get that trivial solution we started with. If we take e to be 1, we get the other solution we had before. And for other values of e, positive, negative, we would get other answers. And these are all the solutions, right? There's nothing else. We solved it, and this is the general solution to this equation. Is there any question here? Okay. Let's make it slightly more complicated. So example number 2, let's solve this differential equation. We are looking for a function y, a function of x, such that the derivative of y with respect to x is equal to y squared. Okay, think about this one, please. It's good to have, if you have a pen and paper or whatever you use, it's good if you try to solve it. So let's think about this for a few minutes, and then tell me if you have the answer. Okay. Okay. So what is the idea here? Does anyone have any suggestion? Okay, I can see the answer in the comments. So what are the steps to solve this differential equation? That is correct. So similar to the previous one, the first step is to separate the variables. Let's separate the variables. Let's move everything which has y in it to left side of the equation, everything which has x in it to the right side of the equation. So we would get dy over y squared. That would be equal to the dx. Right, that would be the first step, right? The second step was taking integral. Again, note that when we take integral, we take integral with respect to the variable which we have dx. For example, it's with respect to x. If we have dy, the integral would be with respect to y. So we have dy over y squared equals integral of dx. Okay, what is integral of dy over y squared? So the first part would be computing this integral. I would write it as integral of y to the power -2 dy, right? And we would have in mind that integral of y to the n dy when n is not equal to -1. This integral is equal to what? Does anyone know what is the answer to this integral? Yes, so that is correct. So it would be y to the n plus 1 over n plus 1 plus a constant. It's pretty obvious here that this does not work when n is equal to -1, because if n is equal to -1, here n plus 1 would be 0, and we can't divide by 0, right? Okay, so here, if we go back, the result of the integral would be y to the power -2 plus 1 over -2 plus 1 plus a constant, which is equal to y to the power -1 over -1 plus c, which is -1 over y plus a constant c. What is integral of dx? Well, that's just x plus a constant. So since these two things are supposed to be equal, we would get that -1 over y is equal to x plus a constant. I would again show this constant with c. It doesn't mean it's the previous c, it's just another constant c. We have two constants, one on the right side, one in the left side. We can just subtract them and we would get this equation. Now we are looking for y. We can flip both sides. So we have -1 over y equals x plus c. If we flip both sides of the equation, the left-hand side would be y over -1, and the right-hand side would be 1 over x plus c, which means y is equal to -1 over x plus c. And that is the solution to the equation. For any constant c, we would have one solution to the equation, and these are all the solutions to the equation. Great. Is there any question here? Okay, let's get to a more general case. So what we are doing here is, okay, there's a comment. So are we considering functions on all of R, or are there any domain restrictions? That is correct. That's something actually I did not mention very clearly. So this is a thing that I've still have not talked about. Sometimes some of these solutions we get, they make sense for every real number. They make sense on all of R. Some of them, their domain is not all of R. Actually, you can just guess that by looking at the solution. So if the solution is y equals to, I don't know, 1 over x, of course, it's either for, x can't be 0. So it's either for positive x, or it's for negative x, for non-zero x, right? I would mention that more clearly in future. That's something we would talk about explicitly, actually. Because the topic is actually, as you know, the main topic is boundary value problems for this course. And the boundary value is exactly referring to that, how much we can extend the domain of these functions. Okay, so what we are doing here, is we are looking at actually what is called first order homogeneous linear differential equations. We are looking at different examples of that. let's make it a little more general. So example number 3, consider the general case of the things we discussed. Well, the generalization of the first example, actually. Suppose derivative of y with respect to x is equal to f of x times y. For a function f from R to R, which here I would assume there should be some assumption on this function. So let's suppose this is a continuous function. Okay, so we have this differential equation, derivative of y with respect to x is f of x times y, and we want to find y as a function of x. Of course, it would depend on this function f. Note that here f is not an unknown function. Suppose f is given. F of x can be x squared. It can be sine of x. It's something, suppose we know what it is. It's the y we are looking for. Okay, think about this one for a few minutes. Okay, maybe it's time for me to explain it. So let's see. Again, what is the first step here? So as you can probably guess, similar to the previous cases, the first step would be to separate the variables. So separate the variables. So we would have dy over y would be equal to f of x times dx. Right? That's the first step. The second step, again, would be to integrate. So the integral of the left-hand side, dy over y, is equal to ln of the absolute value of y plus a constant. The integral of the right-hand side, fx dx, is something. We don't know what is f, so we don't know what is the integral of fx dx. But these two things are supposed to be equal. So ln of absolute value of y plus a constant c is supposed to be equal to integral of fx dx. Maybe I would move the constant c to the other side. Now, because we are looking for y, we don't like ln here, and in order to get rid of that, we would take exponent from both sides. So e to the ln of absolute value of y would be equal to e to the integral of fx dx minus c. Now again, because e and ln are kind of the inverse to each other, the left-hand side is just equal to absolute value of y. They cancel each other. The right-hand side, we would have e to the integral of fx dx because of the properties of the exponent map. It would be times e to the minus c. But e to the minus c is just another constant. Let's denote that with d. So it would be d times integral of fx dx. Now I want to drop the absolute value. If I do that, we should have plus minus on the other side of the equation. Again, plus minus d is another constant. Let's denote that with e. So we get e times e to the integral of fx dx. So this is the solution. These are the solutions to the equations. For different values of e, the constant e here, we would get different solutions. Is there any question here? Okay.
Yeah, I have a question.
Yeah.
Sorry, never mind.
No, well, I mean.
Well, I was just wondering what happens, like, you can extend this to integrable functions, no? Like, does it have to be continuous?
That is correct. So, yeah, sorry. You are perfectly right. So a better assumption here for f would be the function f. We'd like it to be integrable.
Got you. Thanks.
Yeah, I wrote that only because continuous functions are integrable, and it's I thought it's more commonly known what are the continuous functions are, what our continuous functions are. So yeah, so you are perfectly right. We can take integrable functions there. That is true. Yeah, in some sense, yeah, that is true. So yeah. Okay, so let's continue. Let's make it slightly more difficult. Example number 4. Suppose we are looking for a function y such that its derivative with respect to x minus a constant a times y minus another constant b is equal to 0. So a and b are just two constants here. And I think we should assume that, well, if a is 0, we already solved that. So suppose a is a non-zero real number. Okay, think about this one for a few minutes. Okay, let me start. Okay, please look here. So let's see. Here, the difficulty is that b is something non-zero, right? So if b was 0, we would have dy dx equals a times y. We solved that, right? This is the first example we solved. So for a moment, suppose b is equal to 0. If b is equal to 0, we would get this equation, which we already solved that. We know this is the first equation we solved. We know what is the solution to this equation. The solution was y is equal to a constant times e to the, well, here we have a. In the first example, we had lambda ax. But here the difficulty is that b is not 0. So b, but we know here b is not 0 in general. So the idea is to somehow convert this one to the case where the constant or the b is equal to 0. Okay, how can we do that? So we have dy equals dx. Let's take the other terms to the right-hand side, ay plus b. So this b here is non-zero. Somehow, with a modification, I want to do something to get rid of this constant b, right? So since a is non-zero, I can write this down as a times y plus b over a. I can factor a, right? Since a is non-zero, I can do that. If a was 0, that wouldn't make sense. Here we are dividing by a, of course. So we are assuming a is non-zero. On the other hand, note that b over a is a constant, right? Is a constant. And therefore, its derivative with respect to x is just 0, right? So what we can do is I can just add this thing to the left-hand side of the equation, because this is just 0. This doesn't change anything, right? So if I do that, what would I get? I would get dB over A dx plus dy over dx is equal to A times y plus b over A. That's what I'm going to get. I cannot scroll down. Can you all see the last line? Well, I would go to the next page. So what I wrote is that derivative of b over a with respect to x is 0. And we already knew dy over dx is equal to a times y plus b over a. So I can just add db over a dx to the left-hand side of the equation because it is equal to 0 and doesn't change anything. So I would get db over a over dx plus dy over dx is equal to a times y plus b over a. But note that the left-hand side is really equal to d of y plus b over a over dx, right? It's dy plus b over a dx. So if we combine these two equalities, I can see d of y plus b over a over x is equal to a times y plus b over a. That is the equation that I would get. Now, this is interesting because I can do a change of variable here. Note that here I have y plus b over a. Here also I have y plus b over a. So if I define a new variable, so if I introduce new variable, let's show that with y tilde. If I define that, oh, I guess you can't see it here. Well, maybe I should write it up there. So if I define the new variable y tilde to be y plus b over a, this equation would translate to another equation, which is d of y tilde over dx is equal to a y tilde. Now, the interesting thing about this equation is that it is similar to the equation we solved first. You see, there is no constant on the right-hand side, right? There is no plus b anymore. We got rid of that constant. So we have dy tilde over dx equals a y tilde. And we know how to solve this equation. The solution to this equation is just a constant. Let's use d e to the ax, right? But what is y tilde? Remember, y tilde was y plus b over a. So I can just substitute this into the equation. Y tilde is equal to y plus b over a and is supposed to be equal to d times e to the ax. If I take b over a to the other side, I can get y is equal to constant times e to the x minus b over a. And that would be the solution to the equation. I think there is a delay here. Okay, so since y tilde is equal to y plus b over a, and we notice that y tilde is equal to d times e to the ax, if we combine them, we see y plus b over a is equal to d times e to the ax. And therefore, the function y is equal to d e to the ax minus b over a, where this d is an arbitrary constant. And that's the general solution to this equation. Is there any question here? Does it make sense to everyone? Okay. Now, I want to solve this equation from a different way too, which is slightly more complicated. And the reason is not just to waste your time. The reason is that this other method I'm going to introduce is it's a stronger technique, which this technique works in some cases where this solution which I just wrote does not work in those cases. So, and this is a good example to introduce that. So let's look at the same equation, dy over dx minus ay minus b equals 0. Now I want to write down a second way of solving this equation. So this is usually called, I think, integrating factor method. It might look a little bit strange if you haven't seen this before. So let's look at it. So I would just slightly change the equation. I would take b to the other side of the equation. I would get dy dx minus ay is equal to b, where again a and b are constant and a is non-zero. Now, suppose mu of x is a function. Suppose it's a function. We have a function mu, say r to r. Which satisfies this strange property. Well, let me change the viewpoint slightly. Suppose there is such a function which satisfies some properties which we will see. Now multiply this equation by this unknown function mu. So I would get mu of x times dy dx minus mu of x ay is equal to mu of x b. We still don't know what is mu. It's just some function. We are multiplying everything by that. Okay. Now suppose mu satisfies this property. Suppose this function mu satisfies this property. What is that? Derivative of mu with respect to x is equal to minus a mu x. So it might look a little strange. Why am I assuming that? What would I get with this assumption? Well, suppose for a moment, suppose there is such a function. Let's see what we can do. If there is such a function, here, rather than minus mu x times a, I can plug in d mu dx, right? If there is such a function mu, rather than instead of minus a mu x, I can write d mu dx, right? Well, then the equation becomes, so the equation becomes mu dy dx plus y d mu dx is equal to, and on the right hand side we had mu xb. Now look at this left hand side. Can you recognize what is this thing? The left hand side of this equation?
Product rule.
That is correct. It is, you might remember, it's product rule. So product rule in general says if you have two functions f and g, if you take derivative of them with respect to some variable, let's say x, the result would be derivative of f with respect to x times g plus f times derivative of g with respect to x. So I can rewrite the right-hand side. So this, sorry, the left-hand side, it is just derivative with respect to x of mu times y. So our equation becomes derivative of mu y with respect to x is equal to mu x times b. Okay. Now that's pretty interesting. So if we have that, we can actually continue solving the equation. Again, thinking about dx formally, suppose I would multiply both sides by dx. So I would get d mu y is equal to mu x b dx. So now let's integrate both sides. So the last step, we notice d mu y is equal to mu x b dx. If we integrate both sides, we would have integral of d of mu y is integral of mu x b dx. Okay, now the point is that this d, which we call differential, and integral as an operator, these two are almost the inverse of each other. So the left-hand side, integral of d of mu y, they would cancel each other up to a constant. Okay, that would be the left-hand side. What is the right-hand side? Well, we still don't know what is mu, so we can't do anything about the right-hand side, but we can use this expression for the left-hand side. That implies the left-hand side, which is mu y plus a constant c, is equal to integral of mu x b dx. Therefore, mu y is equal to this integral minus this constant c, and I can divide both sides by mu, assuming it's non-zero, at least not zero everywhere, hopefully. Well, we had some property it should satisfy, so we can find what is mu. So we can divide both sides by mu, and we would find y. This is the value of y. But in order to completely understand what it is, I need to find what is mu. If I find mu, I can come back and substitute that into this solution, and we would find out what is the answer, right? So what is mu? So let's remember, what was the property we wanted mu to satisfy? Let's go back right here. Because we wanted to use the product rule, I assume this thing is mu y prime plus mu prime y. So I wanted this thing, which I multiplied y by that, to be equal to mu prime. So derivative of mu should be equal to minus a mu. So the equation was derivative of mu is equal to minus a mu. And again, this is one of those equations which we have seen before. We are familiar with this type of equations. We solve this with separating the variables. I can take mu to one side and x to the other side. And I can take integral of both sides. So this is what we are going to have. The left-hand side would be ln of the absolute value of mu, and The right-hand side would be minus ax plus a constant. And we took exponent from both sides. So the absolute value would be another constant e to the minus ax. And therefore, mu would be plus minus that constant e to the minus ax, which I would show it with e to the times e to the minus x. So now I have mu. I can go back and plug this answer, this solution, to what we had before, right? So look here inside the red box, we have the expression for y, right? So I can plug in what we have for mu. So mu is equal to constant times e to the minus ax. So it's b, another constant e to the minus ax dx minus c. And well, this is a simple integral. Integral of e to the minus ax is just, maybe I would write it here. Integral of e to the minus ax dx is just e to the minus ax over a plus another constant. So if I take this integral, I would get the answer. I would use the constants d1 and d2. It would be d1, say e to the ax, plus, say, d2. This is pretty much the answer we got from the other method. The only difference was that there we also found what is the value of d2, which was minus b over a. Here we can also find the value of d2. You can just simply plug this solution back to the equation, and you can find what is the value of this constant d2. I'm not gonna do that, but this is pretty straightforward. Okay, is there any question here about this method?
So I assume like the reason that we're doing it this way is because we want to extend this to like when a and b are constants.
Well, a and b are constant here. Here I could just do the first method. The reason I did this other method is that this other method works in cases, just like our next example, where the first method does not work there.
Okay.
Yeah, and I thought this is a simple example for this method. So that's a good idea. Actually, I want to look at another example which same method would work. So example number 5, we are looking for a function y such that derivative of y with respect to x minus 3 over xy minus x to the 5 is equal to 0. Well, here I should assume x is positive or negative. Here I would assume x is positive. So try to follow the ideas we had up to this point, see if we can solve this one. Okay, let's continue. So we have our example number 5 was this. We are looking for a function y such that it satisfies this differential equation. Okay, so the first step, I would just slightly, well, I would rewrite the equation. I would just take x to the 5 to the right-hand side. So I would get dy dx minus 3 over x over y and times y is equal to x to the 5. Right. Again, I would multiply everything by a function mu. We call that integrating factor. I would multiply everything by mu. So I would get mu dy dx minus 3 minus mu times 3 over xy is equal to mu times x to the 5. As we saw in the previous example, we like the left-hand side, mu dy dx minus mu 3x y. We like this to be equal to d of mu y dx. This is what we want. Right, this is what we are looking for. Now, the right-hand side by the product rule is equal to the derivative of mu times y plus mu times derivative of y. And therefore, we need this thing here, the left-hand side, the most left side. We need that to be equal to this right-hand side. So if you look carefully, you would see the first terms are equal. They are the, mu dy dx is equal to this mu dy dx. So if they want to be equal, minus mu 3 over xy should be equal to d mu dxy, right? The terms inside green circles are equal. Therefore, the terms inside the red circles need to be equal. So what we want is derivative of mu dx. This is the term in the red circle in the right-hand side. We want it to be equal to minus mu x 3 over x, the other term in the red circle. This is what we want. So for a moment, suppose mu satisfies this equation. Suppose we have it. Suppose there is a function mu such that mu satisfies this thing, right? In that case, if it's true, so remember we wrote down the equation. What we had was this thing. This is after multiplying by mu. So if mu satisfies this equation in the rectangle, it means the left-hand side is equal to mu dy dx, and then minus mu 3 over x is just d mu dx times y, which by product rule, we know it's derivative of mu times y with respect to x. Therefore, derivative of mu y with respect to x is equal to mu x to the 5. Okay, we still do not have the function mu, but we are assuming there is a function mu satisfying this. Okay, is there any question up to this point? Okay, so now again, thinking about the x, formally, we would multiply both sides by that. We would get d of mu y is equal to mu x to the 5 dx. Oops. Mu x to the 5 dx. Now we can integrate both sides. Again, as I mentioned in the previous example, integral and differential are kind of the way they work is like the inverse of each other. So the left-hand side would be mu y plus a constant. The right-hand side, we still don't know what that is, because we don't know what is mu. But anything it is, I can take the constant to the other side. So we would have a constant on the other side. I would divide everything by mu and here we almost have the solution. So if I knew what is mu, then that would be great. I could just plug that into this equation, and then that would be my solution. But I do not know what is mu, so that is the question now. What is mu? Okay, now we want to look for mu. So we want to see what is mu. So looking for mu. So what was the equation we wanted mu to satisfy? Again, let's go back and look at what we had here. In order to do the product rule, we wanted what we have here to be equal to d mu dx, right? What we have here. So we want d mu dx, we want d mu dx to be equal to minus mu 3 over x. This is the equation we need to solve to find the function mu. Again, what we are going to do is we are going to separate the variables. I would take everything which has mu in it to the left side, everything which has x in it to the right side. So d mu over mu would be equal to minus 3 dx over x. Right. Now, what I can do now is I can take integral of the both sides of this equation. So integral of d mu over mu is equal to minus 3 integral of dx over x. But integral of d mu over mu is ln of the absolute value of mu up to a constant. Same thing is true for integral of dx over x. The answer is ln of the absolute value of the x. So the integral of d mu over mu is ln of absolute value of, mu plus a constant, say c1. Same thing is correct for x. Since we are setting them to be equal, what we are going to get is that ln of absolute value of mu is equal to, well, we had minus 3 there outside of the integral, ln of absolute value of x plus a constant c. We take exponent from both sides to get rid of ln because we want mu, not the ln of mu. So e to the ln of mu would be equal to e to the minus 3 ln of absolute value of x plus c. Again, ln and e, they would cancel each other. We would have the absolute value of mu on one side, and on the other side, e to the c times e to the minus 3 ln absolute value of x. Now e to the c is another constant. I would denote that with d. Now here I have e to the minus 3 ln of x. What I can do is that I can say it is equal to e to the ln of x, the whole thing to the power minus 3. Why am I doing that? Because, well, I can see that a little bit easier, that e and ln are going to again cancel each other. Therefore, the right-hand side would be equal to d. Inside the parentheses, I would have absolute value of x, and I still have -3 there. I can drop both of these absolute values, both for x and for mu. That would only give me some plus minus. I would absorb them into the constant I have here. So I would use the constant e to have the plus necessary sign, whatever it is. Now the point is that here we are not looking for every solution to this equation. Remember, if we have just one function mu satisfying this equation, that would be enough, right? Because we want to just use mu to kind of solve the equation. So we are not looking for every solution to this equation. We want to just find one mu satisfying that property, and then we can multiply that equation by that function, and we continue. So I can just take, I will take mu of x to be, well, the simplest thing, just x to the -3. I would take the constant e to be equal to 1. Now let's remember, what was the answer we found? Here we have it. Y is equal to integral of mu of x, which here we can take mu to be, as we saw, x to the -3 times x to the 5 dx over mu plus a constant c over x to the -3, which is equal to integral of x squared dx over x to the -3 plus c over x to the -3. Well, the integral of x squared would be x cubed. There is another, so this would be x cubed plus another constant, say c1, right? So we would get x cubed plus c1 over x to the -3 plus c over x to the -3. Well, maybe I would erase this. Which is equal to x to the 6 plus c1 x to the 3 plus c x to the 3. I would just write both of them there. Is it okay? Let me see. Yeah. Integral. Sorry, so the integral would be 1 over 3x cubed. So it would be x to the 6 over 3 plus a constant c1 x cubed. So the general solution to this equation would be x to the 6 over 3 plus a constant times x to the 3. And this constant is arbitrary. It can be anything. And that's the method for solving these equations. Is there any question here? You want to review what we did here for yourself, maybe, to make sure you can completely follow these steps? So, yeah, sure. So let's, yeah, yes, I will. So let's go back. So this is the equation we started with, right? This is our equation. Now, well, let's look at each step. The first step was I just took x to the 5 to the right-hand side, okay? Now I'm introducing an integrating factor mu. It is just a function. I'm multiplying both sides of this equation by this function. This is what I would get. Mu times dy over dx minus mu times 3 over xy is equal to mu times x to the 5, right? What I like, the reason I'm doing this is that I want to think about the left-hand side of this equation using the product rule. I want to think about it as derivative of mu y with respect to x, right? Again, remember the product rule tells us that derivative, if we multiply f and g and we take derivative with respect to x, it's like taking derivative of f with respect to x times g plus f times derivative of g with respect to x. So I kind of wanted to do the same thing with the left-hand side here. I want it to be equal to derivative of mu times y. This is what I want. I want the left-hand side, I want what I have here. I want it to be equal to this. That might be a hopeful thing, wishful thinking. That might not happen. Maybe it's not possible to find any function mu such that the left-hand side is equal to this. That is possible. But that's kind of a way we are trying. Maybe it works, maybe it doesn't, right? So if the left-hand side wants to be equal to this thing, since d of mu y is equal to d mu dxy plus mu dy dx, these two things should be equal, right? And that tells me, well, since this thing here is equal to this, if they want to be equal, this thing here in the blue circle should be equal to this one. So I'm hoping that I can find the function mu such that minus mu 3 over xy is equal to d mu dxy. That's what we are hoping for. So this is what we want. This is the equation which we have here. Now, for a moment, we assume that there is such a function, right? Before really checking if we can solve this one or not, I'm just assuming there is such a function. So if there is such a function, this equation we had here, the left side would be equal to this. I'm just plugging in what I want to be true, and I'm assuming to be true. I'm just plugging in that into the equation. And then we would get this thing here. And by product rule, that is derivative of mu y with respect to x. If we combine everything I said, it means derivative of mu y with respect to x is equal to mu times x to the 5, which is what we have here. So now I can just think about dx as a formal thing. I would multiply everything by dx, and this is what we would get. D mu y is equal to mu x to the 5 dx, right? Now I can integrate from both sides of this equation. This is what we would get. Now on the left-hand side, integral and differential, these two would cancel each other up to a constant. So if they cancel each other, we would end up with just mu y plus a constant. And the right-hand side, because I do not know what is mu, I would just keep that as an integral of mu x to the 5. Now I would take this constant to the right-hand side, and I would divide everything by mu, and that would give me the expression for y. Y would be equal to this thing. Now, as you can see, the only thing which is unknown in this answer, in order to find out what is y, is mu, right? I don't care about that constant. That constant became anything, but there is still mu here. So I should find what is mu. So the next step was going back to see what is mu. So this was the equation mu is supposed to, this is the equation mu is supposed to satisfy, because we could use the product rule. And we can solve this equation using the separation of variables. I would take everything which has mu in it to the left side, everything which has x in it to the right side. And then I would just take integral of both of them. Integral of the left-hand side up to a constant is ln of absolute value of mu. The right side, this integral, is ln of absolute value of x plus a constant. So this means ln of absolute value of mu should be equal to -3 ln of absolute value of x plus a constant. I would take exponent from both sides to get rid of these ln's. That tells me, and then I would drop the absolute value. That tells me mu up to a constant is x to the -3. I'm not looking for every mu which satisfies this equation. I just want one mu. So I would let e to be 1. So I would take mu to be x to the -3. This is the one I would get. And I would take it back and I would go back to the equation I had. I would just plug in mu with x to the -3. And I would take this integral and I would divide by this mu here in denominator. And that would give me the answer. This thing you would see here is the result. X to the 6/3 plus C1 x cubed. Okay, for an equation y prime plus px y plus, can we just use the rule that integrate? Yeah, we should. I have not really well. Let me look at the question one more time. Yeah, so okay, let's go back here first. Yeah, so we can think about, so this is the question. So we can think about these things slightly more general. We can think about this. Okay, so rather than having these specific things I took, we could think about this equation in a more general way. We could say we have dy dx plus some function of x, say px times y, plus another function q of x equals 0. So here, because I wanted to be explicit, I took specific px and qx. So in our example, px was equal to -3/x, and q of x was equal to -x to the 5. Well, now if you want, you can go back and do the same things in the general case. So if I want to solve this equation in a more general case, I would follow exactly the same steps. I would take q to the right-hand side. I would just multiply everything by this function mu. Now I'm hoping to be able to use the product rule. Therefore, I like this thing to be equal to y d, mu dy dx plus y d mu dx. So if I want to have this equality, this thing here should be equal to this thing here, right? Therefore, mu px should be equal to d mu dx. So mu px should be equal to d mu dx. Therefore, if I take mu to one side, x to the other side, d mu over mu is equal to px dx. I can take integral of the both sides. The left-hand side would be ln of the absolute value of mu plus a constant. I would take that to the right side. Now we are looking for one solution. So if I take exponential of that, it would be c e to the integral of px dx. Sorry, this is not y, this is mu. And I can take, I do not need all the solutions mu, I need just one. I can take that to be, I can take c to be 1, e to the integral of px dx. So that would be the way to do it, sorry, in a general situation. So this is not restricted to this specific example here. For any equation of the form dy dx plus some function of x times y plus another function of x equals 0, we can kind of use the same method. We find this, that's the way to find this integrating factor. And the rest is also similar. This is the function we should multiply everything with using product rule, and the same of the solution is similar. Okay, I guess that is the answer to your solution. Yes, it is e to the integral of px dx. Okay, any question? If not, let's continue. So now we want to think about slightly different equations. Second order homogeneous linear differential equations. So these equations in general are of the form the second derivative of y with respect to x. That's what it means. This is, well, let me just introduce this notation first. This is the, what you might know as y double prime, second prime, prime prime. This just means the second derivative of y with respect to x. d squared y dx squared. So the second order homogeneous linear differential equations are of this form. We are looking for a function y such that it satisfies this equation, the second derivative of y with respect to x plus f of some, for some function f of x times the derivative of y with respect to x plus another function gx times y is equal to 0. For, say, smooth functions f and g, or continuous functions f and g. So how can we solve these equations? How can we solve this thing here? Okay. Does anyone know what is the answer to that? Okay, Anthony, your answer is a pretty good one, but I will get to that. The point is that, so one suggestion is that the solutions are of the form of exponential functions. We can plug in the exponential functions and see if it works or not. Does anyone know if this always works or not? If the solutions are exponential functions or not? Okay, so, okay, I would say it. So the point is that it is not this is not possible to give a general solution for a general second order linear homogeneous equation like this. So the methods, we know they would work for, we would see different examples and different methods to solve them, but there is no general solution. There's no general way of telling what is the answer for any f and g. So no general solution. Now, a very important case is when f and g are constant. So very important case. Is when the functions f of x and g of x are constants. So the equation would have this form. The second derivative of y with respect to x plus, say, some a constant number derivative of y with respect to x plus another constant b is equal to 0. And this is the example we would first focus on. Before solving this example, let me just tell you one simple fact and just a definition before. So before answering this one, let me just tell you one simple thing. So when we have an ODE, ordinary differential equation, so when we have an ordinary differential equation, what we have here is the order of the differential equation. So things we saw up to this point, they were first order. This is an example of a second order differential equation. In general, we can have a differential equation with order n, nth order differential equation, right? It would be the nth derivative of y with respect to x plus whatever equals 0, plus lower derivatives. And the point is that when we want to solve these equations, we might find different solutions, right? So there isn't a unique solution. We might find different solutions. But we would say these solutions are linearly independent. So suppose we have solutions y1 up to, say, ym. We would say these solutions are linearly independent. That means if for any set of real numbers, C1 up to Cm, if we know a linear combination of these things is 0, always 0 for every x, that would imply these constant, all of them are 0. If we have that, we would say this y1 up to ym are linearly independent. Okay? Probably you've seen this thing in linear algebra or similar courses. Okay? That's one fact. The other fact is that when we have a linear equation, like what we have here, if y1 up to ym are solutions, if these are solutions, any linear combination of them is also a solution. So if these things are solutions, any linear combination of them is also a solution. Now, the fact I wanted to mention is that when we have an ordinary differential equation, let's say something like this, something of order n. This is an suppose this is an ordinary differential equation. The point is that at most we would have n linearly independent solutions. Now, this is very similar to the case of polynomials. When you have a polynomial of degree n over r, you would expect to have at most n solutions, right? N roots. This is very similar. Now have that in mind. Let's go back to the equation we had. We wanted to consider a second order differential equation with constant coefficients. Now the point is that these equations always have a solution of this form. These equations, they always have a solution of this form. Y equal to e to some number k times x. There is always such a solution to this equation. So the point is only to find k. So we should find k. In order to find k, I would just plug in y equals to k e to the kx, e to the kx into the equation. So the second derivative of e to the kx with respect to x plus a derivative of that with respect to x plus b should be 0. Now the second derivative of e to the kx with respect to, well, what is that? Well, if you take derivative of y, y prime is k e to the kx, and the second derivative is just k squared e to the kx. So the first thing would be just k squared e to the kx plus. Derivative of e to the kx is just k e to the kx plus b equal 0. Right? Sorry, did I make a mistake in writing the, I wanted to consider the homogeneous one. I think I wrote him, I did a mistake here. Yeah, it's a slightly hard, this is the next example actually, I rushed it a little bit. I want it to be b times y. We would go back, we don't have a constant here. I would go back and add the constant later. It's better to first solve it without constant. So suppose it's b times y. So here we would have b times e to the kx. So there's no constant. There's no constant plus c. We would actually handle the constant the same way we handled it before, but let's first assume there isn't any constant. Now, because e to the x is always non-zero, we can divide this equation by e to the x. So if I divide the equation by e to the x, I would just get rid of e to the x. So I would get k squared plus ak plus b equal to 0. So we have k squared plus ak plus b equals to 0. This is called the characteristic polynomial. And this is quite important actually. So the point here is that we should solve this polynomial to find k. We should solve this polynomial to find k. Now, there are 3 possible cases. Case number 1, we might be, well, what is k? Well, let me first write down what k is. So if I solve this equation, I would see k is equal to minus a plus minus square root of a squared minus 4b over 2. Now define delta to be this value a squared minus 4b, which is under the radical here. As we know, there are different cases. So this delta under the radical, it might be, in case number 1, this is positive. In case number 2, this is 0, and in case number 3, this is negative. If it's positive, it means we can solve that equation and we would get two distinct real solutions. Let's call them K1 and K2. And as I told you, e to the kx is a solution. So here I would have e to the k1x. Let's call that y1. And y2 would be e to the k2x. These are solutions to the differential equation we started with. And because an ordinary differential equation would have at most two linearly independent solutions, and these two are linearly independent, but k1 and k2 are different. So here k1 and k2 are different. These are all the solutions. So any solution is just a linear combination of these two. So it would be c1 times e to the k1x plus c2 e to the k2x. Now in the second case, the roots are equal. We have a root with multiplicity equal to 2. So we would just get one solution, e to the kx. So we have one solution. We hope to find another one, another linearly independent solution. And it's interesting. The other solution is actually, in this case, is just x times e to the kx. You can simply check that if e to the kx is a solution in this case, x times e to the kx is also a solution. And these two solutions are linearly independent. So any solution is a linear combination of them. Maybe it's good to check that. So we already know e to the kx satisfies the equation, is a solution. The claim is that x times e to the kx is also a solution. How is that? Well, let's remember what was the equation. The second derivative of y with respect to x plus a, the derivative of y with respect to x plus by should be 0. Well, this would be the second derivative of x e to the kx with respect to x plus a derivative of x e to the kx with respect to x plus bx e to the kx. Right? So what it is, the second derivative of x e to the kx with respect to x, maybe I should just be slightly, well, what is the second derivative? Let's first compute the first derivative by product rule. It's just e to the kx plus kx e to the kx. Therefore, the second derivative would be just the derivative of what we have above, which is k e to the kx plus k e to the kx plus k squared x e to the kx. So that's the second derivative. So what we had before was the second derivative plus a times the first derivative plus b times the function itself should be equal to 0. Is it equal to 0? Well, let's take a look. So we have different terms. Look at this term, and this term. Okay, so let's group them together. So we have k squared plus ak plus b times x e to the kx which are these terms. And then the remaining part is so we also know that what is k? Remember, k was equal to, what was k? It was equal to minus a plus minus square root of a squared minus 4b over 2. But now we are assuming that this part is 0, right? So 2k plus a is also equal to 0. And this part we have 2k plus a e to the kx, which this is also 0. So the result is 0. Therefore, if k1 is equal to k2, let's call that k, e to the kx is a solution. X times e to the kx is also a solution. So this is one solution, this is the other solution. And these two solutions are linearly independent. And because our ODE is the second order partial ordinary differential equation, it has two linearly independent differential solutions. There is no other linearly independent solution. So the general solution is just a linear combination of these two. Is there any question up to here? Okay. If not, let's consider the third case, case number 3. This is the case where, well, if k is equal to minus a plus or minus square root of a squared minus 4b over 2, this number under the radical, a squared minus 4b, is negative. When it's negative, this radical is not a real number, right? It would be it's not a real number. It is a complex number, right? So therefore, this k would be a complex number. This is a complex number, not a real number. So in this case, two things we would get, k1 and k2 are distinct. They are not equal, but they have a very interesting relation to each other. Does anyone know how these two numbers are related? They are not equal, but there is some relation between them. The point is that they would be conjugate to each other. So these two complex numbers, they are conjugate of each other. So for example, if k1 as a complex number is equal to alpha plus I beta, k2 would be equal to alpha minus I beta. That's a simple theorem about second order polynomials. So if they have a complex solution which is not real, the other solution is the conjugate to the first one. So now we have, the point here is that we have again two solutions. We have e to the k1x and we have e to the k2x. These are solutions to the equation. So y1 equal to that and y2 equals to this. These two are really the solutions to the equation. But the point is that these are not real solutions. They are complex solutions. So if we were looking for complex solutions to these differential equations, we had our answer here, right? But we like to find the real solutions. And the point is that although y1 and y2 are complex, there are certain linear combination of them which is real. So let's find those. So again, suppose K1 is equal to alpha plus I beta, and K2 therefore would be alpha minus I beta. Y1 is equal to e to the K1x, which is e to the alpha x plus I beta x. Now this is equal to e to the alpha x times e to the I beta x. Now e to the I beta x is equal to cosine of beta x plus I sine of beta x. So y2 is equal to e to the alpha x minus I beta x. Therefore, it is e to the alpha x times e to the minus I beta x, which is equal to cosine of minus beta x plus I sine of minus beta x. But the point is that cosine of minus beta x is equal to the cosine of x. So you remember these relations. Cosine of minus theta is equal to cosine of theta, and sine of minus theta is minus sine of theta. So knowing that, this is equal to cosine of beta x minus I sine of beta x. Right? Okay. Now, let's focus on just one of them. Let's just look at this one, for example. This is one solution for the equation, right? So y1, which is equal to e to the alpha x cosine of beta x plus I e to the alpha x sine of beta x is a solution for the equation. Now let's call this one A, let's call this one B. Therefore, we have a solution of the form A plus IB, where A and B are real, but Y1 is a complex one. Now the point is that when we have an equation, a real equation, which has a complex solution, each of these real parts and imaginary parts should be a solution to the equation. So let me write what I said. So when we have a real equation, by real equation, I mean an equation which its coefficients are real. When a real equation, when it has a complex solution, here A plus IB, each part of this thing, both A and B, which are real, they should be solutions to the equation. Well, very, very simple example. Suppose 2x equals 0. Suppose x is a complex number. If 2x is equal to 0, it means if x is A plus IB, both A and B should be solution to this equation. In other words, 2A should be equal to 0 and 2B should be equal to 0. Both parts should satisfy the equation. That's something which always holds. Is that clear? So well, anyway, let's go back to that. That holds for linear things, linear equations. So going back here, this is one solution. This would be the other solution. Here we have a linear equation, and these two parts both should satisfy that. So here we have e to the alpha x cosine of beta x, and this is the real part, and the imaginary part was this one. They both should satisfy the equation. So define maybe y1 tilde to be this one, y2 tilde with this other. Both of them should be satisfying the equation. And they are linearly independent. We have a second order PDE, so any solution should be a linear combination of these. So the general solution is of this form. C1 e to the alpha x cosine of beta x. Sorry, we didn't have x here. Why am I writing beta x? There is no x here. From when I'm writing this wrong? Oh, no, that is correct. Great. I'm not making a mistake. That's great. We do have x here. Plus C2 e to the alpha x sine of beta x. So this is the general form of the solution to the equation. That is for the third case. So if I want to review, the first case was when K1 and K2 are different, but both of them are real. The solutions are e to the K1x, e to the K2x. When they are real but equal, the solutions are e to the K1x. Well, let's call both of them K e to the Kx, and x e to the Kx. And if they are different, actually conjugate each other, but not real, complex, not real, the solutions are, well, if we write this K1 as alpha plus I beta, the solutions are e to the alpha x cosine of beta x and e to the alpha x sine of beta x. These are all the solutions we have. So these are the solutions to the linear equation d squared y dx squared plus a dy dx plus by equal to 0. Note that here a and b are constant and k squared plus ak plus b is equal to 0. So this characteristic equation tells us what are the solutions to these equations. As I mentioned, if a and b here, they are not constant, they are functions, this problem is a lot more complicated and there is no general way to answer this question. Is there any question? Okay, maybe it's a good place to stop because the next part is another topic. I would stop the class here, but I would be around, so if you have any question until 8:30, we can discuss it. Great. So thank you, everyone.